important notations for a chemical reaction of the type AA plus BB that gives CC plus DD. Small letters A, B, C, and D are called the stoichiometric coefficients. In general, we use one arrow to indicate that this reaction is complete and the double arrow for the incomplete reaction. We have to determine the state of A, B, C, and D when we write the chemical reaction, and we will see that is very important in the calculation in the next slides. At the same time t, the number of mole of A reacted divided by A is equal to the number of mole of B reacted divided by B, equal to the number of mole of C formed divided by C, equal the number of mole of D formed divided by D. This is the stoichiometric ratio. And this stoichiometric ratio can be applied at the same time t and at any instant t, or at any advancement of the reaction. Another relation, the variation of the number of moles of A divided by A with the sign minus equal minus delta NB divided by B equal plus delta NC divided by C equal plus delta ND divided by D, and this relation is also applied at the same interval of time delta t. Zeta, by definition, which is equal to this ratio, is the advancement of the reaction in mole at a certain time t. So if we look, for example, to these relations, the stoichiometric ratio is variable, can be applied at any instant t, and at any instant t, we have advancement of this reaction and concentration. Consider the dissolution of KCl in water. Since KCl is a strong electrolyte, it will dissociate completely to K plus and Cl minus ions. So if we start with N0, the initial number of mole of KCl, we have to obtain N0 mole of K plus and N0 mole of Cl minus, and the volume is V total, so the concentration of K plus and Cl minus is equal to C0 equal N0 divided by V total. This is at the macroscopic scale. Go to the microscopic scale. What happens when KCl is dissolved in water? When KCl is dissolved in water, we obtain ions Cl minus surrounded by water molecules and K plus also surrounded by water molecules. And this is, as we said, this is the solvation process. But at the same time, K plus and Cl minus can form what we call ion pair due to the attraction. And this ion pair is K plus directly bound to Cl minus. The formation of ion pair and the interaction water-ion cause the number of these ions the free ions, to be less than the number present. So this value of C0 equal N0 V divided by V is real at the macroscopic scale, but this is not the real concentration at the microscopic scale. So this concentration at the microscopic scale should be corrected. The real concentration or the effective concentration is called the activity, and it's a measurement of the behavior of ions in the solution. This real concentration or activity depends on the nature of the species dissolved, and it depends on the environment of this species, on the composition of the solution, and also on the type of the solvent used. The activity is related to the concentration for ion, and if we have gas, the activity is related to the pressure. And this relation is according to a correction factor gamma. So the activity for ion is directly proportional to the concentration, and the activity of gas is directly proportional to the pressure. And if the substance is solid or liquid, by convention, we use the activity 1. Gamma is the activity coefficients and can be calculated according to the condition of the dissolution, or gamma, we call gamma the correction factor, and this value of gamma is between 0 and 1. If our solution was very diluted, that means Cl- is surrounded by a large number of water molecules, and also K+ is surrounded by large number of H2O molecules. In this case, no possibility of formation of ion pairs between Cl- and K+ due to the presence of these water molecules. For this reason, the concentration at the microscopic scale is real, and in this case, the activity is equal to the concentration, and the correction factor gamma is equal to 1. For a general reaction of the type AA plus BB that gives CC plus DD, the quotient ratio at an instant t or at any advancement of the reaction is equal to the activity of the products divided by the activity of the reactants according to the stoichiometry. One of these times is the time of equilibrium. At equilibrium, Q becomes K, which is equal to the activity of the product divided by the activity of the reactants at equilibrium and according to the stoichiometric coefficients, so according to the stoichiometry. We explained before that for diluted solution, the activity is practically the concentration for ion, so the expression of K according to the concentrations in the diluted solution is given by the following: capital K equal the concentration of C at equilibrium to the power C times the concentration of D at equilibrium to the power D divided by the concentration of A at equilibrium to the power A times the concentration of B at equilibrium divided by B. So the equilibrium constant K is equal to the ratio of the concentration of products on the reactants at equilibrium according to the stoichiometry. For example, if we have this reaction, first of all, I want to ask if this reaction is homogeneous or heterogeneous. Since we have solid and we have several states, this type of equilibrium is heterogeneous. The equilibrium constant is given according to the activities of the products on the reactants according to the stoichiometry. So equal activity Ca2 plus to the power 1 times activity of HCO3 minus to the power 2 divided by the activity of the solid, which is equal by convention to 1, over the activity of CO2 gas. For gas, we use the pressure of CO2 to the power 1, and for liquid, H2O liquid, we also said that we use by convention the activity 1. So this is the expression of K according to the activities. For very diluted solution, we pass from activity to concentration. So the activity of Ca2 plus is the concentration of Ca2 plus. The activity of HCO3 minus is the concentration of HCO3 minus. Since Ca2 plus and HCO3 minus are aqueous ions, divided by the pressure of CO2 to the power 1. Important to say in this example that the activity of CO2 is equal to gamma PCO2, but I consider in this example gamma equal to 1 since my solution is supposed very diluted. In your curriculum, we will pass from activity to concentration. So we use only concentration. We suppose that our solutions are very diluted. From now, when we write, for example, the expression of K or the expression of Q, we will use the concentration for ion and the pressure for gas. And if you remember that we treat this case when we explain the thermodynamics in the first semester, I told you that capital K is the equilibrium thermodynamics. So we said for ions, use concentration, for gas, use pressure, and for solids and liquids, use the term 1. Why? Because K or Q is written according to the activities, and since in our program we supposed that the solutions or our reactions are very diluted, so we pass from activity to concentration and from activity of gas to the pressure of gas. What is the difference between Q and K? For a reaction in solution of the type AA plus BB that gives CC plus DD, the value of Q is equal to the concentration of the products at time t divided by the concentrations of the reactant at the same time t according to the stoichiometry. So how many values of Q do we have for a reaction? For the reaction, we have infinities of value of Q. And we studied in the thermodynamics in the first semester that delta G of the reaction is related to the quotient ratio Q by the relation delta G equal delta G0 plus RT ln Q. And we said that Q depends on the time of the reaction or depends on the advancement of the reaction. And since we have infinities of value of Q for the same reaction, so we have infinities of value of delta G for the same reaction. But one of the times of Q is the time of equilibrium. So at equilibrium, K equal to the concentration of the products divided by the concentration of the reactants at equilibrium, and pay attention according to the stoichiometry. For this reaction, we have one value of K. And as you know, that the equilibrium constant is calculated from delta G0. Delta G0 equal minus RT ln K. So we have one value of delta G0 of the reaction. That means we have one value of the equilibrium constant K. But K and the Q, the comparison of K and the Q, give us indication about the system change of the reaction. The system changes of the reaction is related to Q and K. The system changes such that the reaction quotient Q approach to K. If Q you calculated, يعني Q should be given, is less than the value of capital K, the equilibrium constant with it, which is constant, so the system change in the forward direction. And if Q is greater than the equilibrium constant, the change in the reverse direction or in the backward direction or in direction 2. And if Q equal K, so we are at equilibrium. What is the importance of the value of K? K is calculated from delta G0, so we know the value of K of a reaction. If the value of K is high, so this reaction is advanced in direction 1. And if the value of K is low, this reaction is limited in direction 1. Suppose the value of K is high. Can we say this reaction is complete or quantitative? To know if a reaction is complete or quantitative, the value of K itself is not an indication. It should be compared to a value noted as, which is the domain of quantitativity for this reaction. And as K is greater than this value of S, so this reaction may be considered as complete or quantitative. Any reaction has a known domain of quantitativity. So any reaction has a known value of S. I return to the famous example of titration of monoacid and monobase. First of all, in the college, when you write the reaction between the monoacid and the monobase, you write this reaction as an incomplete reaction. Then you calculated the K of this reaction. And if you find that K of this reaction is greater than 10 to the power 4, you said that this reaction is complete and quantitative. So the value of S, or the value for a reaction of monoacid by monobase to be complete, is 10 to the power 4. If Kr is greater than 10 to the power 4, you consider this reaction as complete or quantitative. What would happen, for example, if you find a value of K equal, for example, 1000? The value of 1000 is high value, but it's less than S equal 10 to the power 4. So if an example you find that K equal 1000, you can say only that your reaction is advanced. But is your reaction complete or quantitative? No, because the value of K, 1000, is less than the domain S, which should be equal to 10 to the power 4. How to know if our reaction is advanced, quantitative, or complete? To know if our reaction is advanced, we have to calculate the degree of advancement alpha, that we call also the degree of conversion. Consider the following reaction. Suppose at t equals 0, we start with A, 0, B, 0, 0, 0. At equilibrium, A will react and B will react. So at equilibrium, A0, we have A0 minus AX, B0 minus BX, CX, DX. We have, for example, two reactants, A or B. So we have to determine on which alpha we want to work to know that our reaction is advanced. Suppose I want to work on the reactant A. Alpha A is equal to the quantity reacted divided by the initial. So it's equal AX divided by A0. And AT equal, AT is the concentration of A remained at time t, which is equal to the initial concentration minus the concentration reacted, equal A0 1 minus AX over A0 equal A0 1 minus alpha A. Then we know the equilibrium constant for this reaction. The equilibrium constant for this reaction is equal to the concentration of the products divided by the concentration of the reactants at equilibrium according to the stoichiometry. And the value of K is known, so we put the concentration of A, B, C, D at equilibrium in their value, and by this way we can calculate the value alpha A. If the value of alpha A is, if the value of alpha A increase, so the reaction is more advanced in direction 1. If alpha A equals 0.99, so the reaction is a quantitative to 1%, we said only that the reaction is a quantitative. And if alpha A found to be 0.999, so the reaction is a quantitative to 0.1%, we say that the reaction is complete. So as a conclusion, to know if our reaction is limited, advanced, quantitative, or complete, we have to calculate the degree of conversion alpha. And we have to choose alpha A or alpha B. In this example, I choose alpha A. If the value of alpha A is less than 0.99, so our reaction is advanced. And if the value of alpha A equals 0.99, our reaction is quantitative. And if alpha A is equal 0.999, so our reaction is complete. And as you see, alpha could not be equal to 1 because in chemistry we don't have 100% conversion. The maximum conversion in chemistry is 99.9. To note also, never forget that the advancement of this reaction can be studied according to alpha B by the same way. I want to write all domains according to the value of alpha. This is the scale of alpha. Alpha equal 0.2 to 0.99 and 0.999. If alpha is less than 0.2, the reaction is limited. And if alpha between 0.2 and 0.99, the reaction is advanced. And if alpha exactly equal 0.999 to 0.998, the reaction is quantitative. And if alpha is equal to 0.999, the reaction is complete. And since alpha 0.99 is close to alpha 0.999, for this reaction, in some books, they don't make the difference between complete and quantitative. They said that the reaction is complete and quantitative, as for example, in college in grade 12. How to know the domain of quantitativity of a certain reaction? As we said before, the value of K is an indication about the quantitativity of a reaction. If the value of K is very high, the reaction is advanced. When the value of K is greater than S, which is the condition of quantitativity, the reaction is complete and quantitative. I will consider an example, a reaction A plus B that gives C plus D. So this is a reaction of stoichiometry 1, 1, 1, 1, and I will start with the same initial concentration C0. Please remember this condition. The stoichiometry is 1, 1, 1, 1, and we have same initial concentrations. So at t equals 0, we start with C0 of A, C0 of B, 0, 0. At T equilibrium, C0, 1 minus alpha, C0, 1 minus alpha, C0 alpha, and C0 alpha. The equilibrium constant is equal to the concentration of C and D divided by the concentration of A and B according to the stoichiometry, which is equal 1, 1, 1, 1. So K equal C0 alpha times C0 alpha divided by C0 1 minus alpha times C0 1 minus alpha. So K equal alpha square divided by 1 minus alpha square. Alpha divided by 1 minus alpha equal radical K. Consider this relation. So K is related to alpha. As alpha increase, the value of K increase. So the reaction is more and more advanced. What is the condition of quantitativity for this reaction? A reaction is quantitative when alpha equal 0.99 and a reaction is complete when alpha equal 0.999. To have a reaction quantitative, alpha should be equal 0.99. Put 0.99 in this equation, you will find that K is greater than 10 to the power 4. And if this reaction is complete, or for this reaction to be complete, put the value of alpha greater than 0.999, so K should be greater than 10 to the power 6. So for a reaction of stoichiometry 1, 1, 1, 1, where the initial concentrations are equal, this reaction is quantitative if the value of K is greater than 10 to the power 4, and this reaction is complete if the value of K of this reaction is greater than 10 to the power 6. Consider K greater than 10 to the power 4. It's the condition of quantitativity for the reaction of mono acid with mono base, and in the previous slides we saw that for the reaction mono acid plus mono base, this reaction is quantitative if K is greater than 10 to the power 4. So 10 to the power 4, this value S, which is the condition of quantitativity for this reaction, is calculated from the relation between K and alpha, and when you put the value of alpha greater than 0.99. If alpha is less than 0.2, we said that the reaction is limited. What is the meaning of limited? A reaction is limited. That means this is a reaction that proceeds with a very, very low yield. When alpha is less than 0.01, so the yield of this reaction or the conversion of this reaction is practically 0. That means if you look to this relation, K is less than 10 to the power 4. K is less than 10 to the power 4 means alpha less than 0.01, means that this reaction practically did not proceed, or it proceed with a yield practically 0, around 0, so we can consider practically we don't have reaction. The quantitativity does not depend only on K. Suppose you have two reactions. The first reaction has a value of K and the second reaction has a value of K. What is the indication of K of a reaction? The indication of K of a reaction is advanced or not advanced. What would happen when you have two possible reactions in the same reaction system? Which reaction begins the first? Do these two reactions start at the same time? We will answer about this question in the next slide. The conclusion, according to the domain of K, we have 10 minus 4, 10 to the power 4, and 10 to the power 6. So if K is less than 10 to the power minus 4, the reaction did not proceed. From 10 minus 4 for K, between 10 minus 4 till 10 to the power 4, reaction proceeds, advancement increase. From 10.4 to 10.6, reaction quantitative. And greater than 10.6, reaction complete. So this is the domain of the quantitativity for a reaction. Pay attention, for a reaction only of stoichiometry 1111, where the initial concentrations are equal. Suppose the reaction has different stoichiometry. So we will have a new figure of K and we will have different domains from that obtained in the stoichiometry 1111.